let's take a look at a little case study that will involve not only string manipulation, but some file I/O. In 1949, Dr. Rudolf Flesch proposed a measure of text readability known as the Flesch Index. This index is based on the average number of syllables per word and the average number of words per sentences in a piece of text. Scores usually range from 0 to 100 and indicate readable prose for the following grade levels. If you have a Flesch Index of 0 through 30, that would indicate a college grade level of readability for the text in question. A Flesch Index of 50 to 60 would indicate a high school grade level of readability, and a Flesch Index of 90 to 100, for instance, would indicate a 4th grade level of readability. We're going to write a program that computes the Flesch Index and grade level for text stored in a text file. Now note that we are not writing the text and then writing it to a file. It is already written to a file. We're going to read it in. So output, let's do our little analysis. Output will consist of the number of sentences, words, and syllables in the file, as well as the file's Flesch Index and grade level equivalent. Input will consist of the name of a text file. Processing tasks consist of counting the syllables, words, and sentences in the file, and determining the Flesch Index and grade level. Now, our interpretation of word, sentence, and syllable for this program is given here. A word will be interpreted as any sequence of non-white space characters. A sentence will be interpreted as any sequence of words ending in a period, a question mark, an exclamation point, colon, or semicolon. And finally, a syllable will be interpreted as any word of 3 characters or less, or any vowel, A, E, I, O, U, or pair of consecutive vowels, except for a final ES, ED, or E that is not LE. Here we have a list of the tasks that we'll have to perform when we talk about counting the sentences. We're going to count the number of the sentences in the text. Count the words. We will count the number of words in the text. Count the syllables. We will count the number of syllables in the text. Compute the Flesch Index. We will compute the Flesch Index for the given number of sentences, words, and syllables. And to compute the grade level, we will compute the grade level equivalent for the given number of sentences, words, and syllables. In particular, we'll have the user enter the file name. So notice that so far we've seen examples where the file name in the open function argument is a literal, but most of the time we see that we'll have the user enter the file name or get the file name through some other means, save it to a variable name, and then when we use the open function, notice we're using the variable file name. Now this should lead you to realize that we could write this program, we could expand it or enhance it so that it could take in many different pieces of text without having to exit the program. We could build a big loop around it. Okay, so we're going to open the file, open file name in the read mode, R. Okay, so the second argument is the mode of the open, how we are opening a file generally for reading or writing, sometimes appending a read-write. And here is our input file. That is the result of the open command. The file is created, the virtual file that is in our program. Next, we get to the read, right? So we're just going to go ahead and process the entire contents of the file at once. Input file read, and that will be our text. So we have a huge text string. Well, probably huge. Next, we're going to start with counting the sentences. So using string processing methods, we can do this fairly easily. Also given the kind of definition that we gave sentences. So we can simply say text.count the periods plus text.count the question marks plus the colons plus the semicolons plus the exclamation points. And this should give us a count of all the sentences in our file. It's just that easy. Next, we're going to count the words. This gets to be a bit more complicated. So we'll make use of the split string method, right? If you recall, without any argument, the split string method will divide up all the so-called words in our text according to white space, tabs, new line characters, etc. It will return a list of these words. Here, actually, I'm sorry, not a list. This isn't the list yet. This is actually the length of the number of words. So we're not even going to deal with the list of words at this point. We're just going to get its count. So when we take the length of the list of words that this returns, we get the count of the words. I'm going to go to the next slide. I inserted an extra slide here because the division in your author's example was kind of unfortunate. So I basically cobbled together. Now we come to the point in the program where we actually have to count the syllables. And I want you to notice something about the structure of the code at this point. Notice that we have an accumulator syllables, and of course we are initializing it before the loop. It would make no point, it would make no sense to initialize the accumulator inside the loop where it would be reset each pass, and we wouldn't come out with a total sum or count or anything else. So something to keep in mind, don't forget your accumulators. They're not part of the loop syntax or even the loop maintenance, but they may be very much a part of your problem maintenance. So always think when you're putting together a loop, do I have one or more accumulators? And did I in fact initialize them before I entered the loop? So that takes place here. And then we have our typical for loop. But notice, we not only have this for loop, but we have 1, 2, 3 for loops. So we have 2 for loops nested inside the outside for loop. One thing that you should be aware of is that the innermost for loop will execute repeatedly many more times than the middle for loop. All right, many more times than that. This middle for loop will execute many more times than the outer for loop. All right, and we could, if we think about spinning around in these loops, the innermost for will be spinning the fastest. The middle one will be spinning a little less fast or a little slower, and then finally we have the outside loop that spins the slowest of all. Notice also, we've mentioned before that you can nest any sort of structure inside of another structure in Python and most programming languages. So we see that we have for loops nested inside each other. We also have selection statements nested in this for. And in fact, the selection statement that follows this nested for is nested along with this for inside another for loop. So we've got lots of levels of nesting, combinations of selection and loops. This is a nice little code snippet for you to sort of practice with and study and analyze. Now, there are some things that are pretty clever going on in this piece of code. There are other things I'm not so crazy about. Here we have our for loop. Remember the syntax: for control variable in sequence. So this is quite nice. We have our control variable word. Remember, there's nothing sacred about the name that we give the control variable. It should just make sense in terms of our usage of the variable. And this is perfect, because what we'd like to do next is iterate through each word within the text. And what does text.split give us? The split method, remember, splits up the entire text into separate words. And remember, we're using the definition of word, where simply a word is a group of characters that is delineated by a white space, one or more spaces or tabs or new line characters. And when we split the text, the return value of this method is in fact a list of the words in the text. A list, or another way to call it is, it would be a sequence. So we have for word in the sequence created by the split method, which is quite handy. So we'll be iterating through each word. Now we go to the inner for loop here, and what will we be doing? We'll be iterating now through a sequence of characters. Notice that here we're not using a range expression, we're not using a method to give us or produce a sequence or a list. We have manually created a sequence, a list of characters, using the square brackets and commas, and we know that each of the elements of this particular sequence, each is a character, because it's delineated by quotes. Each one is inside quotes. So what are we doing here? We're taking each vowel one at a time, and we're going to take a count of the vowel in the word. And we're going to say that every time I find a vowel, I'm going to bump up the number of syllables in the word. Now, I want you to see also that on your author's part, this is a bit imprecise, to say the least. If you were to have a word like there, T-H-E-I-R, where we have an E and an I together, that's one syllable. But because of this imprecise algorithm that we're using, it would be considered to be two syllables. So please notice that there are a number of imprecise things in your author's algorithm. Personally, I think he could have done a somewhat better job. But then again, he is trying to keep the example short. It certainly is illustrative. However, I think if we sat down and thought about it, we could perhaps come up with a somewhat better algorithm for this. Now, in addition to counting the vowels, we look to see, do we have some endings where we don't want to add to the vowel count. So here we're going to ask if we find an ES, an ED, or an E, and if the word actually ends with that set of characters, we're going to subtract one from the syllables. So we are recovering some of these, although in some cases these endings may actually cause the word to have an extra syllable depending on pronunciation. But across the board, we're saying if the word ends in this, it does not add an extra syllable to the word. So we subtract one. And then finally, regardless of the ending, if the word ends with LE, we're going to consider that to be an extra syllable. The notion being something like whistle. So that would be an extra syllable, even whether or not it makes an extra syllable. All right. So Sometimes this is going to be right, other times it's not going to be right, but that's the algorithm nonetheless. We have the term 206.835 minus 1.015 times words per sentences. So we have a term, we have a factor, right? We have another factor. So we have a words per sentences factor, a syllables per words factor, and a flesh index term. I would expect when you were encoding this that you would actually make all of these named constants. Remember, we do not allow magic numbers. The only literal numbers we allow in your program are 0, 1, sometimes -1, or when you're formatting, you can use whatever numbers you need to do the formatting properly. We see the same problem here with computing the level, right? We have the words per sentences factor for level. We have here the syllables per words factor for level, and we see the term for level. So you would have to make each of these, unless you wanted to get points off, a named constant, not a magic number. Finally, we'll be outputting the results. The flesh index is, and we'll be outputting index. The grade level equivalent is, and output the level. And then we would print the count of the sentences, the count of the words, the count of the syllables, and we would be done. Next, we come to the testing phase of our program. Now, I've been trying to encourage you to do what's known as incremental development, where we start with the restatement of the problem, we do a little analysis, we determine what we have to do, what are our outputs, what are our inputs, what are our tasks. Then we start design. So far, we've been following pretty much a top-down pattern of development. And in fact, in general, it is encouraged that software engineers do top-down design, top-down development, but, and this may seem odd, bottom-up integration. And as part of bottom-up integration, you might do some bottom-up testing, where you actually take a little part of your program, not the whole thing. This is sometimes called unit testing, and you test that little portion first before you integrate it with the rest of your program. So using bottom-up testing, each task is coded in testing before it's integrated into the overall program. And after you've written the code for one or two tasks, instead of putting it all together, you actually use something called a driver to test them in a short script. For instance, on pages 152 and 153, your author has an example where he's pulled out this the code that computes the index and the level. And what he's done is he's put a little driver in front of it that simply takes in a number of sentences, a number of words, a number of syllables. In other words, just completely bypasses the idea of getting the text and analyzing it. So it just gets in the counts and computes the index and the level by itself. This would be an example of bottom-up testing. And so if you use this strategy, you would first check out these sort of formulas, etc., and show that you're getting the expected results for given for given inputs. And once you have established that, then you would integrate this code into the remainder of your code. Notice that the rest of the code, the first half has to do with the input to the program, and then the middle portion has to do with the analysis itself. So if you were to continue this bottom-up testing, you might very well then complete the analysis portion of the code and have a little driver that tested that. For instance, one that fed a known piece of text to the analysis, and then you could see that you got the expected results. You got the counts that you expected.